Part 2 of this lecture will begin looking at expressing solution concentrations in units based on the number of moles of solute. We'll specifically look at molarity, molality, and mole fraction. Now, before starting that, we want to do a little mental exercise here that will be helpful. Suppose you had two containers containing two different aqueous solutions. We have a 1 liter of solution on the left, 1 liter of solution on the right. Both of these have these red spheres in them, and we're going to pretend that these red spheres are actually dissolved and that we can see each one of them. We have a couple of questions to ask about these solutions. The first would be, which of the solutions has the higher number of dissolved solute particles? Well, that should be easy. Let's just count the red spheres in each one. So there's 22 red spheres in solution A, 26 red spheres in solution B, so therefore solution B contains the higher number of dissolved solute particles. That was easy. The second question is, which of the solutions has the higher concentration of dissolved solute particles? Well, let's take a look at this. Solution A contains 22 red spheres in 1 liter of solution, so we could express the concentration in spheres per liter of solution as 22 spheres per liter. Using the same concentration units for solution B, we have 26 red spheres in 2 liters of solution, which would come out to 13 spheres per liter. So we find that solution A is more concentrated than solution B, despite having fewer dissolved solute particles. And this is because the solute particles in solution A are dissolved in a significantly smaller volume of solution than in solution B. Now, this whole exercise and the answers to these questions may be obvious to some or all of you, but this is an important distinction to make and keep in mind going forward. Let's start out and discuss molarity, which is the number of moles of solute per liter of solution. As mentioned previously, this was introduced in General Chemistry 1, or should have been, and we're going to reintroduce it here and expand on its usefulness as a concentration unit and examine its relationship to other common concentration units. Let's consider this scenario. A student weighs out 95.882 grams of glucose and manages to dissolve this in about, the tilde here means about 200 milliliters of water in an open beaker. The solution is then quantitatively transferred to a 500 milliliter volumetric flask and diluted by addition of water exactly to the mark, the white ring on the neck of the 500 milliliter flask. This volumetric flask is then capped and inverted about 20 times to ensure complete mixing. Let's determine the molar concentration of glucose in this 500 milliliters of solution. Well, molarity, remember, is defined as the number of moles of solute, in this case glucose, divided by the number of liters of solution. So let's determine the number of moles of glucose present in the solution, and that's pretty straightforward. We have 95.882 grams, and we effectively divide that by the molar mass of glucose, and we get 0.53223 moles of glucose. We're then going to convert the milliliters of solution, the 500 milliliters, to liters, and that's pretty straightforward. 500 milliliters would be 0.5 liters. And so the molarity of this solution is the number of moles of glucose divided by the number of liters of solution. And here we get 1.0645 moles per liter, or 1.0645 capital M. We can get away with this number of significant figures here because the precision on the numbers we've used up till now is pretty high. Well, let's make some notes about what we just did. Now, when attempting to prepare a solution of precise molarity, which is what we did up here, it is good practice to first dissolve the desired amount of solute in a volume of solvent that is noticeably less than the final desired volume of solution. That's what we did here. We took our solute and dissolved it in only about 200 milliliters of water in a beaker. Then we diluted to the final volume by taking this solution that we made, quantitatively transferring it to a volumetric flask, and then adding water until the total volume of the solution was exactly 500 milliliters. In the particular example here, we would end up actually using less than 500 milliliters of water. Remember, this is 500 milliliters is the volume of the solution, which is the solute plus the solvent. And since the solute here would take up a fair amount of volume of that solution, we would actually use less than 500 milliliters of water. So remember, molarity demands that you know the volume of the solution, not the volume of the solvent alone. The phrase quantitatively transferred used in the example problem is important. This means you need to find a way to get that initial 200 milliliters of solution from the beaker to the volumetric flask without leaving any dissolved glucose behind. It's fairly easy to do, but you have to make sure you do that. And of course, this should go without saying, but all aqueous solutions that you actually care about in a laboratory should be prepared only with distilled or deionized water. And clean glassware is helpful. The definition of clean can vary by individual, though it shouldn't, and can be a source of conflict in a lab. Let's have some more fun with molarities on the next slide. You can count the number of individual molecules and or ions in a solution using molarity and solution volume information. This turns out to be very helpful to be able to do this and relates back to that illustration we just did involving the counting of red spheres on a previous slide. Recall the definition of molarity. Molarity is the number of moles of solute divided by the number of liters of solution. If we rearrange this, we find the number of moles of solute is equal to the molarity times the number of liters of solution. We see moles equals moles per liter, molarity times liters. Liters would cancel, giving us moles. So you can count the number of solute particles by simply multiplying the molar concentration of the solution by the volume of the solution in liters. So let's consider two aqueous solutions of glucose. In solution A, let's suppose we have 200 milliliters of total solution, and the solution concentration is 0.1455 molar. Solution B, we have 285 milliliters of a solution that's 0.1255 molar. Both of these in glucose, of course. So we ask which solution contains a larger number of glucose molecules. Well, in solution A, the number of moles of glucose would be the concentration of this solution, 0.1455 moles per liter, times the number of liters. I've converted milliliters to liters, and we get 0.02910 moles of glucose. Solution B, the number of moles of glucose would be the concentration of this solution, 0.1255 moles per liter, times the volume in liters, equals 0.03577 moles of glucose. So similar to the illustration we did in slide 7, the less concentrated solution actually contained a greater number of solute particles. And again, as in that previous example, this is simply because the more dilute solution has a significantly higher volume than the more concentrated solution. Common sense check. If the volumes of the two solutions were the same, the more concentrated one would naturally contain the greater number of moles of solute. Now, just to be annoying, we could use Avogadro's number and convert the number of moles of glucose in each solution to an actual number. Here's what I mean. In solution A, we know there's 0.02910 moles of glucose, and we can use Avogadro's number to convert this to the actual number of molecules of glucose, 1.75 times 10 to the 22nd molecules of glucose. Solution B, we take 0.03577 moles of glucose, multiply by Avogadro's number, and get 2.15 times 10 to the 22nd molecules of glucose. I hope I've been calling this glucose through this whole problem. If I haven't, my apologies. It's glucose. So we can see the number of molecules of glucose, even the actual count here, is greater in solution B. Let's look at some more applications of molarities on the next slide. Let's suppose you're interviewing for a temporary contract job as a lab technician. After filling out all the paperwork, the interviewer brings in a 250 milliliter volumetric flask filled exactly to the 250 mark on that flask and containing a blue solution. The flask has a label on it that says 0.0750 molar copper nitrate. The interviewer asks you to describe how you would use this solution to make 500 milliliters of a new aqueous solution of copper nitrate that has a concentration of 0.0160 molar. The only catch here is that you cannot involve the direct use, you cannot use the trusty old dilution formula, but you are allowed a calculator and a pen and paper. Well, the first thing you want to do, of course, is not to panic. Here's some steps you might propose to the interviewer. You might want to calculate the number of moles of copper nitrate needed to make 500 milliliters of 0.016 molar copper nitrate. This is your target solution, and you'd like to know how many moles of copper nitrate do you need in that 500 milliliters to make this concentration. The number of moles needed would be the concentration of the target solution times the volume of the target solution, and this would give you the number of moles of solute, in this case, of course, copper nitrate, needed for the target solution. Next, you could calculate the volume of the solution that he gave you, the 0.075 molar, that's sitting right in front of you, that will contain this many moles of copper nitrate. You could do that by rearranging the molarity equation in a different way. The number of liters of solution needed would be the reciprocal of the molarity of the 0.0750 molar solution you have to work with times the number of moles of solute required for the target solution. All I'm doing here is taking the reciprocal of the concentration of the solution you have in front of you and multiply by the number of moles of copper nitrate you need. Moles of copper nitrate cancel out, and you get 0.107 liters of solution, which would of course be 107 milliliters of that solution that's sitting in front of you. So what you would do is quantitatively transfer 107 milliliters of the 0.075 molar copper nitrate from the 250 flask over to the 500 milliliter flask, and then use water to dilute to the mark on the 500 milliliter flask and mix, and you're done. Suppose then the interviewer asked, How would you go about quantitatively transferring 107 milliliters of solution from the original 250 flask to the 500 milliliter flask? Oh, now you might panic. Only kidding. This is where all your careful attention and effort in your chemistry lab courses will help you. And I know all the students I've ever worked with are all carefully pay attention to everything that happens in lab. Now, just in case you haven't used the dilution formula that I referred to on the previous slide that you couldn't use in your interview because they didn't want you to use it, they wanted you to figure out another way. Here's how you could have solved that same problem using the dilution formula. Recall from the previous slide, what you want to do is calculate the volume of the solution they put in front of you, the 0.0750 molar copper nitrate, required to prepare 500 milliliters of a 0.0160 molar solution. Well, the dilution formula has the form M1V1 equals M2V2, where M1 here would be the molarity of the original, what we call stock solution, in this case, the 0.075 molar solution that they put in front of you. V1 would be the volume of that stock solution required to make your target solution. And so V1 is what we're trying to determine. M2 would be the molarity of the target solution, which they gave you as 0.0160 molar. And V2 would be the volume of the target solution, in this case 500 milliliters. So you simply solve for V1, put in M2, V2, and M1, and out pops 107 milliliters. A couple things to note here. When using the dilution formula, you can, if appropriate, leave the volume units as milliliters. You don't have to convert to liters first. And what seems really obvious here is that the dilution formula seemed incredibly easier than following the reasoning on the previous slide. So if using the dilution formula is such a simple way of getting answers to questions like this, why would you ever approach the problem in the manner outlined on the previous slide, besides the reason of the interviewer telling you you couldn't? Well, the answer to that is that it will be very handy in future material, especially in acid-base titrations, to have a fundamental understanding of counting molecules and/or ions in particular solutions. The approach used on the previous slide, in my opinion, will lead to the required fundamental understanding that will aid in comprehension of future material in the course. There is nothing wrong with using the dilution formula where appropriate. However, and what I found is that it's not uncommon for inexperienced students to use it in situations where it's not appropriate. Where that normally comes up is for titrations, which we'll cover in the future, that involve reactions that are not simple one-to-one reactions. Now let's examine one more example of using calculations involving molarity to count molecules and/or ions in solution. In particular, we will look at counting ions. So let's do some more counting, in this case the counting of ions. And as our example, we'll once again consider the 500 milliliters of 0.016 molar copper nitrate solution that the interviewer asked you to make, or at least describe how you would make in the previous examples. Let's calculate the following things about this solution. The first would be the number of moles of copper nitrate present in the solution. The second would be the number of moles of copper 2+ ions present in the solution. And then finally, the number of moles of nitrate ions present in this solution. It would be good for us to recall what happens when copper nitrate dissolves in water. Copper nitrate solid dissolving in water will produce copper 2+ ions and nitrate ions. And you can see here from the formula of copper nitrate that each copper nitrate will produce 1 copper ion and 2 nitrate ions. We can now calculate the number of copper nitrate formula units, basically, present in this solution by simply taking the concentration of the solution, 0.0160 moles per liter, times the half liter of solution gives 0.00800 moles of copper nitrate formula units. And this should look familiar from a previous calculation. How about the number of moles of copper ions? Well, the number of moles of copper ions would be again equal to the molarity of the solution times the number of liters of solution times the fact that you get 1 mole of copper ion for every mole of copper nitrate that dissolves. We get that from the coefficients of this balanced equation. 1 copper nitrate produces 1 copper ion. And so we'd calculate that the solution would contain 0.00800 moles of copper ions. And this makes sense, 1 copper ion per copper nitrate. How about the number of moles of nitrate ions? Well, concentration of the solution times the half liter times the fact that the formula and the equation tell us that you'd get 2 moles of nitrate for every 1 mole of copper nitrate that dissolves, which would give us 0.0160 moles of nitrate ions. Again, this makes sense. 2 nitrates produced for every copper nitrate that dissolves. So if the label on the 500 milliliter flask says 0.0160 molar copper nitrate, keep in mind that there's a lot of hidden information behind this label. In this case, the hidden information is that the solution does not really contain intact copper nitrate units, but in fact rather contains 0.00800 moles of copper ion and 0.0160 moles of nitrate ion. Now, in reality, the situation in the solution is not quite this cut and dry, so we will slightly modify this view in upcoming slides. In part 3 of this lecture, we will move on to discussing molality and mole fraction.